Okay, the second part of this chapter 4 about the FreeRTOS API. So I was talking about how to create a task and how to delete the task. It's very simple. It's not so difficult, as you can see. So here I'm going to talk about priority of task and preemption. So here you have an example with an idle task. So that's the task when no one task is running. Then you have a high priority task, event based. So it was he gonna run. It will be ready on an event. You have a median. That's periodic. So it's periodically running, and a low priority also event-based when you receive a message or there's an interruption, etc. It's not periodic, as you can see, and it's asynchronous. And this one is periodic. Okay. So in this example, we can see that the task 2 is running at the beginning. Then there's no task running, so it's an idle task. It's running. Okay. When the task 3 is receive an event, it will be ready, and because there's no other task with running, it takes a priority about the idle task. We have the lowest priority, so task 3 preempt, that is preemption, is preempting the idle task and is running. Okay. Then when it's finished, when it's waiting for another event, it go back to the idle task. Then after that, for example, there's an other event on the task 3, so you're gonna run another time, like here, and takes a hand here. And then, for example, if here there is another task 2, we have the high priority than the task 1, it gonna run. It takes a hand, it takes a priority about the task 3, and we call it preemption. So the task 2 here preempts the task 3. And when it's finished, he's waiting for an event, he go back to the task 3, which was interrupted here. Okay, so you go back, then you go back to the idle task. And for example, there is an event, or there's the periodic time, the time to wait is occurring. Here, the task 2 is preempt the idle task. But for example, here, if the event makes the task 1 ready, it can also preempt the task 2, like this. Okay, the task 3 here preempt. When it's finished, it go back to task 2. And here, for example, the blue event processing is delayed until every high priority task are suspended or blocked. Okay, here you can see several tasks with preemption, priority, etc. If you have two tasks with the same priority, okay, task 1, task 2, if they are all the same priority, so task 1 is running, is in a running state, and runs until scheduler preempt it for task 2. So after an amount of time, if they are the same priority, it will give a very fair time to each task. As you can see, each task has the same processing time to run. So the time here moved down to here. The scheduler gives a hand to T at this time to make the task run, and etc. Then it go back to task 1, task 2. We call it a round robin algorithm. Okay, that is the name of this. Okay, I already talked about it, but here I'm gonna talk with more details. A real-time operating system always needs a timer to generate a ticker that will allow the scheduler to manage the time. To generate here, there's an error, is a tick. We're gonna correct it. A tick. Okay, we call it a tick. And this timer is commonly called tick system or system tick. It depends. It's a ticker, for example. And the value of the system tick varies from 1 to 20 milliseconds. It depends on the application. Okay. On the ESP32, the system tick is set to 1 millisecond by default. Okay. So that is so each tick it calls the scheduler. We will see it later here. So so the ticker creates an interrupt and calls the scheduler to choose the task to run. So, for example, you have the time, and when there's a ticker interrupt of the timer, it leave the task which is running, it go to the interruption, and here the kernel is deciding which task to run. It's a scheduling here, okay? It calls the scheduler, and the scheduler choose the next task to run. For example, here it go to the task 2, and you run until the ticker is running, and that is each 1 millisecond. Okay, so each 1 millisecond, it can decide which task is running at which time. Okay, if we want to delay a task, there's also an API, and it's called vtask delay. And here the value that you enter here is a value in numbers of tick. Okay. For example, if you want to delay, if we have our ticker configured on 1 millisecond, and we want to delay it from 100 milliseconds, we put 100 here. Okay. For example, here we can have a task which print each 100 milliseconds this message on the serial link. It would hello from task 1, and then it delay for 100 milliseconds. And with Arduino, that is the same as delay 100. It's the same, okay? We can see here also on the FreeRTOS site. Here you have more explanations about it. Here you have an example. Okay, you create a delay. Okay, also, yeah, you can have this delay directly in milliseconds if you put 500 divided by per tick period millisecond. Is this a value? To give this delay directly in millisecond in place of tick numbers, because perhaps it can vary this. So if this vary and you put like this, it will be blocking for 500 milliseconds. Here is to toggle LED, so to make blink a delay LED each 500 milliseconds. Another example. Then last slide, sorry, to pass a parameter. Okay. We want, for example, give a parameter to a task. So, for example, a string. So we declare a table, task1 parameter, and we put a string of ASCII numbers, ASCII values, sorry. So the task1 params. So here, when we create a task, we give as argument this parameter, okay? So we say here with for table, we don't need to put the A. If we don't put the brackets here, is the address that you give. And then it will receive this in the parameter. So you can do like this, serial print, this one, and then you will have this message printed in the task. So here is only an example to see how you can give a parameter to a task, and then here another printing each 1 second as for the example. Okay, that was the end of this chapter 4 about the FreeRTOS API. I hope that you enjoy it and that you understand what all the things that I want to explain you. If you have question, you can ask it on the communication channel.